Oh, all right.
So
Um,
today we'll have David Joss telling us about algebraic factors. Let's welcome him.
Thank you. Hi, thanks. Hi. Um, okay, so yeah, today I'm going to talk about algebraic patterns, which is something I really like. I've talked about them a little bit before at Topos, but I like them a lot. So I'm going to talk about them, and I'm going to try and talk about them a little more intuitively than technically, which is, maybe is not that exciting, but I think I like developing the images behind what the technical stuff is as a guide to doing the actual sort of hard-hitting technical stuff later. So uh, with that said, I'm only going to give one fully concrete example of an algebraic pattern because they're actually a bit difficult to set up, but they're nice to have once you have them. Okay, so the idea of an algebraic pattern is that it's a category of pasting diagrams. And a pasting diagram is something like these that I've prepared in advance. So the left-hand side here is an example of a pasting diagram for categories. So this picture here represents the composite, if you will, H after G after F. Um, it's a in the idea being that we might actually write this in the boxes if we were to write them in the boxes, right? FGH. Then we think of this picture as saying that we have this composite, and it represents that composite really only when we put it in one big box at the end. So really, I would say that this picture here represents that composite. And so, okay. Similarly, here we have, say, the pasting diagrams for multi-categories. And here I wrote the pasting diagrams for props or symmetric monodal categories. And you can imagine that we can do this for pretty much any sort of essentially algebraic theory that we could come up with a way of doing these. Maybe we couldn't actually draw them on the plane anymore, and they wouldn't be like nice string diagrams like this. But you can imagine us coming up with different kinds of diagrams of this sort. And so the idea of an algebraic pattern is to neatly divide the combinatorics of these diagrams from the algebraic structure that they encode on the for this corresponding essentially algebraic theory. So it's of pasting diagrams plus structure, which encodes a sketch, codes a limit sketch. Um, in the case of, these finite diagrams, it will be a finite limit sketch, and that's our essentially algebraic theory. So there are two kinds of morphisms in an algebraic pattern. The first are called inerts, and these are subdiagram inclusions. So as an example, I have this diagram here, and then I have our friend from before, and I can consider the inert subdiagram inclusion in red that, say, picks out this half here. Of course, there's also there's another one, right? So there's, there's the other one, blue, right? Is that other one. And there are no more subdiagrams. I can't like stretch it. I can't miss pieces in the middle. They have to be well-formed diagrams that are subdiagrams of other diagrams. So I'll say that the for categories, right? I'm going to give that a little more. definition. For categories, we're going to say, I will say these form a category. So a cat called, uh, so a category P is going to be my algebraic pattern for pasting diagrams, called P inert. And the objects are the diagrams and the morphisms are inert. So for categories, P is going to end up being delta. So P inert will end up being this category delta inert, whose objects are natural numbers, and where a morphism or finite non-empty ordinals, and where a morphism is if you will, a distance preserving inclusion. So distance preserving inclusion. So the idea is that each one of these chains of beads here corresponds to a finite non-empty ordinal. The ordinal is the wires. So the diagrams we're look at this. The diagrams we're looking at here are like, oh, there's a home button right there. I see. Um, there's a wire, there's one, there's two, and so on. It's indexed by, so this is known as 0, this is known as 1, well, this is known as 2, and so on, and that's the indexing. We write them with brackets like this. Okay? And then the maps are these distance-preserving inclusions. They are subsequences of these sequences. Okay. So it gets harder and harder to define these the more complicated it is, but no matter what it is, it's always subdiagram inclusions. So now there's a thing we can already start to learn about this, which is like note, observe, diagrams are usually built out of basic components. Basic or elementary components. So the elementary components in the case of categories are the wire and the single box. And of course, a general one of these pasting diagrams for categories is a sequence of single boxes glued together along incident wires. For some of the other structures here, right, the elementaries for categories are like there and there. I'll claim this is cat. For multicat, cat, we have the wire, and then we have a few other different kinds of boxes. So we have one of them corresponding to each arity. So there's not necessarily finitely many elementary boxes, right? But note that every tree in the multi-category case, so the objects, I should say maybe for P inert, when we're looking at categories, it's these sequences. For multi-categories, it's trees. And for props, it's directed acyclic graphs. Open directed acyclic graphs, if you will. Just as all sequences are built out of single jumps here, all trees are built out of the various branching shapes. And all DAGs are built out of, again, open DAGs, so like DAGs that can have dangling edges, if you will, are built out of shapes that are of this form. Where you have some number on one side and some other number on the other side. And all of these diagrams up there are built out of these pieces, right? So we can think of a functor, so a contravariant functor I'll say I should say, by the way, that algebraic patterns, the idea is due to Chu and Haugseng, and I'm not going to use their conventions because I find them unintuitive. So so for Chu and Haugseng, a this would be covariant, but for me, I'm going to use contravariant. Functor P inner op to set we can think of as a labeling L. So that L of P is equal to the set of labelings of the diagram P. And if that's to be true, that when a diagram is actually built up out of elementary pieces, then to label a diagram, you should only have to label each of its elementary components, right? So the sanity check on labelings is called the Siegel condition, is that LP is going to be, it has a canonical map to the limit over all, uh, over what I'm going to call the elementary diagram of P, which is just equal to the elementaries in P sliced over P of, let me call it E in here, by which E, of course, means both E and an inert, an elementary and an inert in there, but I'm just going to say that. And we're just going to have to label the elementary. So the Siegel condition is that the Siegel condition says that this is an isomorphism. In other words, it says that to label a diagram, it suffices to label all its elementary components, but you have to check that those labels coincide in the right way. So in other words, to label a diagram like this one above here, right? To label this, right, I would have to label all of its elementary components. So I'll draw them above. We have the left wire, the middle wire, the right wire, and each bubble. I then also have the inclusions like this. And this category, this little category here, that's what I was calling L of this. This is the elementary diagram associated to this pasting diagram. And that's a diagram where pasting diagram I'm using as a primitive term to refer to the objects of the algebraic pattern. This is a diagram in the ordinary categorical sense. Okay, so to label this one here, like the way I would label it is I would write A, B, C here, and I would write F and G, and F has to be, so now let's see what that means, right? That's how I would naively label it. And so this I'm labeling A, B, C, and then this I'm labeling F, and this I'm labeling G. But of course, to label this elementary diagram, I also have to label the edges here. And the fact that this is, in fact, that this is going to form a limit diagram with respect to these inerts says that the label I'm going to choose for this left component here has to pull back to the label there. So that's the idea. So, so this is how we end up with the notion of, so I'll make a definition, a p-graph is a pre-sheaf, or just a functor out of, contravariant functor out of, p inert satisfying the Siegel condition. And I will note that the Siegel condition is evidently it's a limit condition, and so this can be described as a sketch, limit sketch. In fact, it's a very nice way to get a sketch because all we had to do was pick this full subcategory of elementary objects. Then we define the limit diagram to be the full slice category of maps from our subcategory into our objects. Of course, for this to be a limit sketch, you'd have to take you'd have to take P op because
Mm.
you know, but something always is annoying if you. So one way to I can describe what how to think about P op, which is that we can think. I'll give that other description because I think it's nice and I like it as well. So that was intuition for. We're not yet at the other kinds of. We haven't done any algebra. We're just doing bookkeeping now.
The
Um,
blueprint. Oh, yeah.
exactly. So now I'm going to tell the other intuition, which is like intuition for P op inert for P inert op. And instead of saying that the objects are, so this is a, can also be intuition for P, but it's a, or P op, but it's a dual intuition sort of. That well, now we'll say that the objects are contexts in a dependent type theory. So where the elementaries, these are primitive types. So e.g., the primitive types we have in the theory of categories is object and morphism. But to define morphism, so this is these are what we call here rules. Um, Object, and then we have so these are two rules, and we see these rules as giving us the elementaries, where the structure of the rules themselves also tells us about the inerts. So so the inerts are going to be, in this point of view, are going to be the so-called weakenings, or forgetting some variables. So in this case, right, the wire here corresponds, instead of the wire, we write x of type ob to refer to an object. And instead of the box, we write x of type object, y of type object, f of type morphism x to y. And then you note that there are two maps, and now it's sort of evident that they should go the other way, you know? In here, we had two maps like this, and here we're going to have two maps like this. Again, this is intuition for the opposite category, so we're intending them to go the opposite way. And here, where these two maps are going to be the projections here. So what, as a map of context, it's going to be a substitution. So we're going to write out X, the codomain in terms of the domain. So, sorry, maybe I'll, yeah, go up a little bit. So we're going to get X gets X, and then here we can get X gets Y. Um, in other words, these are the possible substitutions that only use that only exactly use the variables verbatim, i.e. substitutions only consisting of pure variables. Okay. So we'll come back to this because yeah, it continues going on. As I said, this is a way of thinking about essentially algebraic theories. Another way of thinking about essentially algebraic theories is uh, uh, dependent, so freely generated dependent type theories. Okay, cool. So in that case, right, a map here now, just to say L, now L of X of type ob gives you the set of specific values, specific values, x can range over. And similarly for all the other ones, right? The Siegel condition now says that the Siegel condition says that the values that a list of variables can range over is the limit of the variables that each individual variable can range over, um, which is sensible. Okay, so good. So now now let's do something. Let's get active. Actives.
Is it a pun?
Yeah, that's my pun. The actives are the other kinds of morphism in P. And they are actives are the other morphisms in P, and they correspond to uh, actual operations in these theories. So graphically, this means this is these can be described like diagrammatically. Grammatically, these are given by nesting, right? So an example here, I'm going to give an active. So we've seen the two inerts you have between these two. But there are also a few actives between these two. Um, so here's one of them. By the way, for active, I'm going to put a bar on the other end. How do I select? Is this a selector? Oh, let me move it down a little bit. There you go. So in active, what I'm going to do is I'm going to take every elementary diagram in the domain, and I'm going to fill it with a subdiagram of the codomain. So for here, I'm going to draw, the easiest way to do that is to just draw the codomain again, and then just draw the domain over it. So here I'm going to draw like this. So that's one. Here's another. And then there's actually, I believe, even some more. If you can see what they might be.
Like a thin box.
Yeah.
Like it's a box that contains no boxes in the codomain, right?
Yep. So again, I'm going to draw this. Now I can put all of these in one box, but I can actually put nothing in this box.
Okay, I see.
And
So
yeah,
there's another also like nothing on
the other side.
Okay.
Yeah. But we can't actually fit it in the middle, I don't think. Because you have to draw this diagram has to cover the whole diagram here.
Okay.
So
So
yeah.
we can't have like two empty boxes, like only
Right.
two ends.
Because the reason we can't have that is because, or like we can't have them each take one but not cover the middle one, is because everything in the second diagram has to be within something of the first diagram. So for example, no to this. Like this is not valid.
Okay.
It's not at the right height. You know, that middle one is not covered.
Okay.
So it turns out that in delta, this has a very easy description, despite the fact that it seems these rules are meant to tell you how to generalize them to sort of general pasting diagram things, like if you look with trees or other things. But with delta, it's pretty easy. It's a map f n to m is active in delta if it preserves endpoints. And remember that we are indexing by the number of wires. So all we need is for the left wire to go to the leftmost thing and the right wire to go to the rightmost thing. Whatever else happens in between is just determined what parts of the codomain get swallowed by which parts of the domain, but it's not uh it's not, it doesn't get involved in this. Whereas I think it can get more complicated if you use a more complicated. Okay, so diagrammatically they're nesting. Type theoretically they are terms. They correspond to terms. So as an example of this, there's a well, maybe I'll write out. Should I write these out?
Yeah.
So in here, I have to write out my, let's say, X, Y, Z of type objects, and F and G of types morphism. But that's too lazy. I hope you'll let me get away with X, Y, and D of type object, but then I'll write this as more X, Y, and G of type more Y, Z. Okay, and then over here, I'm going to have X, Y, Z, W are objects, and then I'm going to have F, I'll just write it as X to Y, easy here, Y to Z, H, Z to W. Okay, so that top picture, right? Again, in this point, it's going this, the intuitions are opposite. So with this picture, again, it's a substitution. So I'm going to have to substitute in, for every one of these values, I have to substitute in some expression in these. So the first thing to note is that x is getting x here. I'm setting it to the same thing if I labeled it, thinking about it this way, right? And then let's look at what y gets. So y is the middle one here, but in this one here, it corresponds to the third value. So that's actually getting substituted by z. And then what was z gets substituted by w, the last value. Meanwhile, what was f, as you can see, is getting substituted. F is the first box on the picture. It's getting substituted by the composite of the first two here. So it's getting substituted by G after F. And now you can see we actually did use, finally, we used a term in our theory. So this is where you actively do something in the theory. And G is here just getting substituted by H. And that's the full description. Nice. So I wonder if maybe it's a good idea if you wanted to do the other one, like, one of these other ones.
Yeah.
No. I don't know if you want
one of the ones where you
write it
have
up.
empty box, there's a
That's a good trick, yeah.
This one.
Yeah, try that one, yeah.
So first of all,
Excuse me.
x is substitute like this one, right? So it's like y.
X is
No.
from left to right.
Oh, sorry.
Yeah, if I draw them, I'll draw them on here. This is X, F, Y, G, Z, and then this is X, F, Y, G, Z, H, W.
So this empty. Oh, where is it?
Yeah. Well, it's not so much empty, it carries the wire through it, if you will. The wire cuts across it.
I can't draw in like horizontal.
Yeah, do you want me to draw it and you just tell me?
Okay.
Because
So
I
does it
know
mean that
this
like the
stuff's hard
first
to use
one,
here. Yeah, X. So what is the first object?
y?
I disagree.
Oh,
I disagree because Y, if we draw it into the picture, right? The original picture is actually these three things. So the original picture is actually all in here. So it's actually this X, this is F, this is Y, this is G, this is Z, and this is W.
sorry. So okay. So yeah, this is x. You mean
Yeah.
this?
So this one's also X. Yeah,
Oh,
that wire is also
okay.
an X.
So
Yeah.
x to x,
Yep. And then
y
Y,
to x,
uh,
y to x or x to y.
nope, that's right. Sorry, I'm just having a
Okay. And then
thing.
z and y. Yeah, yeah, this one.
That gets that is going to get
This is w.
the final edge, yeah. So we're taking the features on the left-hand side and we're substituting them in where they get matched over by the stuff on the right-hand side.
Mm. Okay.
So the W wire is still the furthest right wire. On the left-hand side, that was called Z. So we have to replace Z by W.
Okay. Oh, okay. I also
Oh,
wrote
sorry.
it.
Okay.
Okay.
Good luck. Okay. So now you have the two other features you have to substitute in for are the F and the G.
Yes, but we have an empty here.
Yeah.
What should we do? Like nothing.
Well, let's see. That empty, so that F is getting sent to some morphism that goes from X to X.
Mm-hmm. Like an identity?
I mean, there's nothing else you could do, right? So yeah, so we'll take it to be id X, and then G is getting sent to,
G is getting sent to
or like G is getting set to, I should say. Like a
like
G is defined to be.
this F.
F is just the first of the ones on the left. Whereas G here, right, if I draw it out, the F is this little box and the G on the left-hand side is something. Maybe I should have named them all different names. But
Bit confused with yeah.
let me if I name them all different names, maybe it
See,
becomes easier.
this G is now becomes this big three
Yes.
combined together. So we
Yeah, yeah,
got
yeah.
the composite of all
Yeah,
three.
exactly. So G after F. Cool. So that's how you see that here we have um, terms like id X and composites like this are terms, and those are corresponding to the actives in this case.
Okay, so it's like flipped it. So we substitute like here. Okay, we change from F to the identity, but I have to go from the identity to F.
Yeah,
Okay, I see.
yeah. So the contravariance here is that we're thinking when we think about these pictures, the pictures we think about this as sort of like maps between diagrams, where the inclusions are maps between diagrams in a sort of obvious way. And these are sort of weird maps where every feature, every elementary feature on the left is sent to a sub-diagram of the right. But it still feels like a map in that direction.
Okay.
Meanwhile, when you're thinking type theoretically, everything's dualized. So instead of thinking of them about diagram inclusions, we think of them, instead of thinking about them as diagrams, we think about lists of variables that might range over what the diagram is describing, right? And then what was subdiagrams become essentially projections out of these products, selections of some variables out of them. And then what are these swallowing up of these subdiagrams are given by composition operations of a variety of forms. Right? And so,
like it's a very good tool here that like another way to look at like actives that they're the opposite of like morphisms, like a morphism on boxes over here and the boxes over here is the same thing as an active the left term and field.
Yeah.
And so it's sort of very visible with that picture of elements of delta.
Then are there any relationships between inerts and actives?
Yes. Although I want to say one thing.
Okay,
Um,
let's continue.
I want to say like when I said like yeah, it had to be it X, right? What else would you do? Let me justify for you that it actually behaves like the identity. So how do we compose actives? Well, we double nest and then we erase the middle feature, right? So let me give you an example of that, which is here's I'm gonna take the composite with this active that I'm gonna draw up here. There's only one, and it has to be the one where I put both of them together. Well, is there only one? Yeah, it is. There is only one. And I have to do this one,
Okay.
right? And that, by the way, corresponds to just the pure composition of two morphisms.
Yes.
So now let me do this one followed by this one, right? So I'll draw. So first I draw the very far one. Then I draw the middle one around it. And then I draw the outer one around it, like that. Right?
Okay, so they overlap.
And then that's twice nested. So then I erase the middle line, the middle boxes. And that is the unique one that goes from here to here. Right?
You mean like to this one to the whole
Yeah.
thing? Okay, yeah.
And it corresponds, if I call this, if I say this is x, f, y, then this corresponds to f gets h after g after f.
Yeah.
And you can see that the identity that I composed with the identity, and I got exactly what I was composing with. So this is what proves to you that the identities work, that it must have been the identity. It works like the identity there. Um, and I hope you can see that these images work just as well if you, instead of putting, you can make little trees in here instead, right? And nest trees or nest other kinds of shapes, right? You can take diagrams like this, and then you could have, diagrams inside them. And then it still works. This story I'm telling you still works, depending, no matter sort of what pictures you're putting in these. Okay. So now how do actives and inerts interrelate, as you asked? Well, there is a way that they relate that is implicit in the story I've already told you about actives in both of them. So I'll do both of them and I'll tell you why I must already know something about it. Again, we're going to pick an active to study. So I'm going to pick this active. Like that. And now, how do I know that active looks like that? Well, let's say that I want to look into an active and I want to see its parts. And what I said is that what an active does is it replaces every elementary feature on the left with a subdiagram on the right. So what that means is that if I have an elementary over here, or in fact, if I have any subdiagram over here, because we could just piece them together, but for now, I'll just do an elementary. So there's my inert here, right? Now, what I can do is I can look into that box and look into the active and say, I know which subdiagram I get, right? So I can put in here, I can induce this subdiagram here, right? And then there's an obvious induced active here, which is just the restriction of the active to that part.
Okay, so it's like the bottom one restricted. Okay.
So given A and I, we're getting this thing which I'll call I star A. And as you can see, this lets us rewrite the order of them because we have I and then A, and we can rewrite it into A and then I, or like an active and then an inert. And this actually is going to constitute a factorization system active inert on P. And in general, there's no better way to describe the algebraic pattern than saying it has two kinds of maps and they together form an F factorization system in this way. So it's actually also nice to just look at this and say, in fact, there's a double category, which I'll call double cat, which I'll call active P, which is given by squares of that form. So it's P inert and then inerts vertically, actives horizontally. I'll call this S, I'll call this T. So it's a double category, and because I have this factorization thing, this thing here is in fact a discrete fibration. And that's if it's a strict factorization system, otherwise it's a groupoidal fibration. Yeah, we could see this as well in the type theoretic picture. I don't know if that's useful, like what this looks like, what the factorization looks like when we do it with type theory. So, right. So again, here it's I'll actually use different names for everything, so it's a little less confusing this time. Would that be better? So this is going to be X, Y, Z of type ob, F, X to Y, G, Y to Z. And then this one here is going to be A, B, C, D of type ob. Um, uh, uh, R, A to B, S, B to C, T, C to D. There we go. So it's the same thing as before, but now these ones are labeled X, Y, Z, and these ones are labeled A, B, C, D. And then, right, the active here, again, everything's backwards. The active here is given by, excuse me.
Yeah, we have technical problems with it. We are back now.
Yeah.
Let's continue.
Yep. So here, I'm going to have you fill out the rest of this one.
I'm trying to understand.
Right.
So
now on this one, just to make it less confusing, I've called this F, Y, G, and Z. And I've called this A, R, B, S, C, T, D. And so now they're in different namespaces and it's a little less overlappy.
yes. So we are considering this below 1, right? And so X gets substituted to A, and this Y gets substituted to C. So I should write C point. Wait, so yeah, the laptop is being naughty. Sometimes it jumps to the top, but sometimes it works. Yeah.
Okay, we're back after some technical difficulties.
Yes. And I will try to do this. So C gets to G.
Mm.
And
That's a Y. Sorry.
oh yeah. Y and Z. So it's D to Z.
Mm-hmm.
And then F. So it's the composite of what are these two?
R and S.
R and S.
Mm.
So SOR gets to F. And this is T. It gets to G.
Mm-hmm. Yep,
Yeah.
exactly. So,
Oh, let me scroll down.
it jumped back up.
Yes, but I think it's okay. I just as long as
Yeah, that's exactly right. So if we put in here, I'll just erase this part. So if we put in here,
sorry, I find that even if you operate,
and if I do it, it jumps up.
yeah.
Right.
Okay.
Yeah.
I'll print this.
Okay, yeah. Let's continue. So what's here? The top right corner. So let me try. So it's like this one. So I think we have A, B, C, O. Well, I think writing like
Do you want to, you can
No,
write
no.
on the other one if it's easier to actually do.
some practice in order to write
Yeah.
nicely. So they are the object. OB. And we have RS. Right?
Mm-hmm.
And let me try to do this one. The top horizontal map.
Mhm.
So let's move a bit. Okay. So this one is X. So X sends to let me see. The things like A, right? This is Y, right? Yeah. And so we have C gets to Y.
Mm-hmm. I like to say Y gets C, or like the way to think about it is sort of that we're setting the Y is being set by the value C.
Okay. Thank you. And also this box is labeled as F. So F gets to the two together, which is R and S. So SOR.
Yep.
Yeah.
And so one thing to note is you can see, just as you can see, is there like a way I can laser point? No? Okay. Just as you can see that the verticals that I've drawn over here, the inerts, are subdiagram inclusions, you can think of this as a subactive of this other active, right? And in that way, you get this nice sort of double category picture. I'll zoom down a little bit. It looks like these squares, double category of these squares, and they compose on either end because they're just commutative squares somewhere. Is one way to think of it. But you also have this extra property, which is that you can complete the square in this way. And in fact, it does have a universal property. It makes the source map, which projects out the source of a horizontal or an active. This thing I'm going to refer to as active P1 also. One. Um, that the source map is a discrete fibration or a groupoidal fibration, depending on how strict you like your factorizations. So if it's a strict factorization system, then that will be an actual discrete fibration. A unique factorization system, I should say. Right. Right. And so in we can, excuse me. Okay, so now, right, if we take a functor P to set L such that L satisfies, or by the way, I'll name this here inert. Let me call the inclusion of inerts into P J, not I, J. To match my notes. Satisfies, or like restricted along J, satisfies the Siegel condition. Then this is called a P algebra or model of P. How am going to call it Sieg P for a Siegel object. But right. Okay. Of course, you could just take the Siegel condition on P itself. You could see this as a sketch structure on P itself. In fact, it's rather nice to see this here as giving us an F sketch structure on a category. And that only matters if we go to cat, but it's still rather nice. So if we do P, sorry, these should be opt by my earlier conventions. So P opt to cat is when we look at it like this, for example, let me look at delta, right? Delta to cat, if I I'm going to call this L, such that L restricted along J satisfies Siegel condition. That is the same thing as being a strict double category. Or generally, I mean, it's generally true that delta with the sketch structure we've put on it through the algebraic pattern is the sketch for category objects. So this is a category object in cat, but it's actually quite nice to know that if we want, for example, to describe a lax double functor is a lax morphism of models of the F sketch, delta, inert, including into delta. Sorry. And so the reason is that let's look at what that means, right? A natural transformation of so if L goes from delta op to cat, so recall that a lax morphism of models of the F sketch or of just F functors um, is a lax transformation formation, or like I guess we're going to call it L and M. No, L to M phi, right? Which is strict on inerts.
Mhm.
And so let's think about what that is, right? I have, for example, I have L, this thing, M, this thing, and I have L wire, M wire. And here I have, say, L of 0, the left leg, let's say, and then this is M of 0. And here I have phi. And you can see that on the left-hand side, I have the category of morphisms of L, the category of objects of L, the category of morphisms of M, the category of objects of M, and this is the source projection. And then to say that this commutes is to say that phi, which acts on both objects and morphisms, actually strictly preserves source and target, source, target, and all of the other bookkeeping laws. But now, if I put instead now we know that by the Siegel condition, maybe I'll give myself a little more room here. Oh no. Okay, well. Oh no. Um, yeah. By the Siegel condition, okay, I'm happy. All right. Okay. By the Siegel condition, this is given by the following pullback over the elementary diagrams, right? And this one too. And indeed by the universal property, we know that this is actually phi, phi. This is phi. This is phi. And now, however, I want to take L of this, the active, right? Right? And now this is actually supposed to be a lax transformation. And so what you can see is that this is actually going to give us a morphism from the phi of F, if I do a dot here, phi of G, it's going to give us a two cell into phi of F dot G, where this is dot and this is dot for the respective double categories we're talking about here. Okay, so that's just to say that like one other nice thing about this presentation of algebra of essentially algebraic structure is that it naturally lifts to higher categorical settings. It contains the same information you need to do the correct kind of higher category theory as encoded in the point of view of F sketches and F categories. Okay, so I have one more thing I guess I want to say. I think. There's a couple things I could say, like how models of the double category in span cat are virtual models in the virtual double models in the sense that if you do it for delta, you get virtual double categories, which is kind of cool. Or I could tell you about the monadicity, how the double category relates to the monadicity. So I think I want to do that one. So remember that our double category here is P inert. And then this is here is is diagrams of this form. P inert. Okay. And this I'm calling S and T. So um, my claim is that um, uh, so remember that also J is going to stand for P inert into P. So my claim is that the monad, is that presheaves on P is going to be the algebras for the monad. Well, this is not related to anything special. J upper star, J lower bang, J upper star, J lower bang, where this is left con extension. Because J is identity on objects, which is good enough. And that two, so that's one. Claim two is that J upper star, J lower bang is actually equal to S lower bang, T upper star. And this actually has a nice um, uh, interpretation, right? Especially when we think about this. Yeah. Especially when so one thing to note, right, is that what's nice about this second one, which I'll prove in a moment, but if we just understand it, remember that this thing here is a discrete vibration by the factorization property. So what we're doing here is I'm going to take my L, I'm going to work with vibrations now, and this is going to be a discrete vibration. In other words, we're instead of doing presheaves, I'm going to do discrete vibrations. So T upper star is given by pullback. All right. But now
Sorry, so this L is
the Grothendieck, maybe I'll call it the Grothendieck construction of L. It's the discrete vibration corresponding to the category of elements of L. And this is the Grothendieck construction as a transit of that, right? And as it turns out, if you have a discrete vibration, the composite here is in fact S lower bang of T upper star of L, or the Grothendieck construction. So if you have a discrete vibration, right, post-composition by it corresponds to left Kelvin extension along it. This is just one of those things, which I guess I could go into. I didn't prepare on, but this is like the thing to one of these in the like dictionary between the discrete vibrations and presheaves. This is like one of the useful features, which I believe becomes more shaky in two categories world. But regardless, right? So,
So yeah, like in general, you do post-composition, and then you need to turn the result into a discrete vibration. And the thing you have here is that post-composition will already be a discrete.
right. Okay. Great. That's a great explanation for this. Thank you. Uh, um, excuse me. Sorry. It's a dry cough. Right. So, what this is saying then is that every double category does in fact induce a monad on the slice categories by composition with it. And what this is saying is that if we restrict to the discrete vibrations, we're actually getting the left con extension monad here. So in the case, let's see what happens. Let's see what this means for this for delta, right? In that case, then we have delta inert, right? And then again, we have these things here. Okay. Yeah. Right. Okay. So now let's take a L and put it here, right? And let's look at the fiber over, say, 1, just for simplicity. So over 1, it's L, which, by the way, is this thing. It's this one, right? Over here, it's that. So it's the arrows of this. Oh, sorry, I'm doing this the wrong way. Let's see what the result, let's see what the resulting thing is. We have to work backwards. Oh, I'm gonna. Okay. Okay, so now over here, let's look at 1. And then let's look at the fiber over all of this thing here and try to understand what that is, right? So the fiber of that is going to be the sum of the fibers over this first leg, S, right? So let me look at S inverse of this, right? The fiber over here. That's going to be all actives out of that 1, right? So it's actives out of it to something. It equals this, excuse me,
Okay.
instead of that. Yeah. And so the actives out of 1, if you like, you have to be boundary preserving. So you have to send those 2 wires to the endpoint. So S inverse of that will actually just equal the natural numbers. In other words, it's going to be 1 for every copy of these, because we could put every diagram exactly once into that. There's a unique active out of 1, right? So here we have that. And then over that, we're going to pair that with, so over here we have all the natural numbers. So this is, my natural numbers. So then over, say, n here, right? So this, say, for example, maps down into here. Over here, right? The map, and I'll note that it's really this active out, so I'm going to box it up like that. There we go. That's how you know it's an active out of 1. And now, right, what is the fiber of this pullback here, which I didn't fully draw? Well, the fiber over a pullback is always the fiber over the image, right? So whatever this up here is the same thing as mapping this down this way, right? In which case I'm taking the target, which is what's inside the box. So this is just n here. And then we look at what's over here, which is L. Like that. So in total, we have that this fiber up here is the same thing for every choice in there. So in fact, what we see is that S bang T upper star L at 1, for example, is equal to the sum over n of L of n. And that is the construction you would expect for the free category monad, right? You take you take the graph you would get, and you take the graph you would get if you shoved all the paths into the edges. And that's what we're doing. We're replacing the set of edges by the set of paths. And if we did it for multiple ones, well, it will turn out that, by the factorization property, it sort of breaks down. which is not a general feature of algebraic patterns. So this is something special that's going on here. And so it is not always the case, by the way, that this is the free model monad. In other words, this is a monad on presheaves, but it's not always the case that it preserves being a model for the pattern, or that it preserves being the Siegel conditions. And that's a special feature of delta and things like it. So anyway, should I prove this fact?
If you'd like to.
Otherwise, I'll be done.
I'd be interested in.
Cool.
Okay.
Here's my version of the proof where I just ripped someone else off for most of it. So here's a theorem that I learned from Hackney and Koch in their paper on free decomposition spaces. For them, what they do is they do it in the, for them, they consider this span instead. And this is, I think, also much more similar to what's considered in the actual Chu Haoxing paper, but I find it quite difficult to read this part of it. So this span, and I'm going to call this D and C for domain and codomain, not to confuse it with the other one, which was S and T. For this one, right? So my claim is that again, my claim is that J bang is equal to D bang C star. Okay. So pull back along C, push forward along D. It's worth noting that D, this is still a discrete vibration. Right? Okay. It's still a discrete vibration. Yeah. Again, by discrete, yeah. Okay. The lift is again given by factoring. Okay. So what do we do? Well, note that this has a right adjoint, which I'll call I. I'm calling it I because what it does is it's going to send an object to the identity on it. And so because we have C is adjoint to I, we therefore have that C upper star is equal to I lower bang by adjoint foo. But also we have DI is equal to J. Why? Because the functoriality of I just sends an inert to the identity square on that inert, and when you then compose by the domain, you just get the obvious inclusion J. So J bang is equal to D bang I bang is equal to D bang C star. Okay, so that's their lemma there, which is nice. And now what we can do is just sort of arrange this in a little square, and we'll restrict it to get the one we wanted. Ah, crap, I keep doing it wrong. Active, inert, P inert, P inert, P inert. This is going to be J. This is equals. This is going to be, they're both inert this time. This again was called source and target. This was called domain and codomain. And this here is the evident inclusion, which I will note is a pullback. This left square is a pullback. Right? Because I'm literally just restricting that left-hand side to be in the inert subcategory. And so So, right, we note that J star, J bang equals, by the left thing, J star, D bang, C star, right? But then by Beck-Chevalier, and using that the left square is a pullback, right? Let me call this K. We note that this is the same thing as J star D bang is the same thing as S bang K star. Beck-Chevalier. And then I have my C star. But then C star, K star, that's just equal to T star. So there you go. There's our proof that the monad is like that. That's the easy part. The tricky part and the much more interesting part, which I think we'll save for later, is that when does this preserve the property of the Siegel conditions? And so this is what, I mean, maybe I could keep going here, but this is like, but I don't have a good answer for it totally. I have a good hunch that we've been thinking about, but I don't have a good answer, so I don't know if I should say it. I'd try, maybe. Should I just say it?
I'd be interested in.
Okay.
I mean,
It's what I mean.
talk about.
It's what we've talked about.
Yeah.
So, I don't know if it requires a lot of build up. Maybe it doesn't. Right. I'll try and say it, and we'll see how we go from here. The brief idea, right? So the point is that to note that the left con extension restriction monad is in fact given by push-pull along this double category, which is really quite nice because that push-pull is like very easy to compute, right? You know, very concrete to compute. You get a really good sense of what's going on there. So the problem is, the question is, when is S bang T star, when does S bang T star restrict to models of P inert and not just pre-sheaves on it? And the answer must be by the theorem in Chu and Haug saying when this algebraic pattern is so-called extendable. But I'm going to try and put it in a frame. This is something I've been talking about with Jason that uses this double category directly because it's actually should be quite nice to do so rather than fiddling too much with con extensions.
And so just by this, you mean, so obviously the monad can always, oh, right. So when you start with a model, you can do S bang T star.
Yeah.
You still get something which is a model.
Yes.
On the end. Okay.
Yeah. And because algebras for the monad, we already know that algebras for S bang T star are pre-sheaves on P. All we need to know is that they are also models. We know that by this sort of fact I didn't prove, that if you have an identity on objects functor, it's the resulting push left con extension restriction adjunction is monadic. Perhaps you can believe. Of course, you can be even more general than identity on objects functor by using the fact that pre-sheaves can't really tell what objects the site has. So the true statement is that everything in the image is a retract. Everything in the image is a retract of something in the domain. But that's essentially as far as you can tell. That would imply that their Cauchy completions could be chosen so that they would become identity on objects. It's bijective on objects. Anyway. Okay. So,
okay.
Sure. Should we? Okay.
Okay.
Yeah, might as well.
Okay.
All right.
Okay.
Tease. Teasing. All right. Yeah, do it one day.
Yeah, so thanks, Jax, for telling us so much about algebra patterns with concrete examples and work through all the details.
Thanks, Joanna, for finding a great audience. So there you go.
So,
Okay.
thank you.